Welcome to this video. We are going to see how sound can be represented using a sine curve, even though sound waves don't have crests or troughs. Sound is longitudinal. That means that the shape of the wave looks like this. There are regions that are expanded, or rarefactions, and there are regions that are squished together, or compressions. And that compression-rarefaction pattern repeats for a simple sound wave. Yet, when we draw standing sound waves in pipes, we use sine curves which have crests and troughs. This seems wrong because, after all, sound waves don't have crests and troughs. They have something different, compressions and rarefactions. So what do these sine curves mean? The simple answer is this. The transverse wave that we draw illustrates where the longitudinal nodes and longitudinal antinodes are located within the pipe. Now let's see that this is actually true. Here I have a bunch of particles. Now currently there is no wave in the particles, but I want to produce a sound wave and show you what the sound wave looks like in the particles after some time has passed. Instead of just creating the compressions and the rarefactions, I'm going to use a sine curve to create the compressions and rarefactions. So there's a rule for how this works. The higher the sine wave, so right here the sine wave is really, really high up. The higher the sine wave, the farther right the particle. So this particle would be pushed really far to the right. And likewise, if the sine wave is down below the center point, the center line, then that means the particle here would be pushed really far to the left. Now, something we need to know first about sound is this. If you produce a sound wave, and then you look at the air, the particles aren't all displaced the same amount. Otherwise, we wouldn't have compressions and rarefactions. Instead, there are different displacements for different particles at a single snapshot in time. Here's what that means. Some particles have been pushed really far, others have been pushed not so far, and others haven't moved at all. Now, this is important because what I'm trying to do right now is produce compressions and rarefactions based on the sine curve. And I want to be consistent in how far I push particles. How will I know how far I need to push or move the particles? I will use this bank of arrows. These arrows will tell me. The shorter arrows, here and here, are what I'll use when the sine curve is not very high. These represent small displacements when the sine curve isn't very high. And the longer arrows I will use when the sine curve is really, really high, representing larger displacements. So let's get started. The first particle is not displaced left or right because the sine curve is at 0. It has no height. The second particle, what about this one? The sine curve does have some height, but the height isn't very large. So we're going to use one of the small arrows. Because the sine curve has positive height, I'm going to use a small arrow pointing to the right. So that first particle, I'm going to move it over to the right. The second particle will be moved over to the right a small amount. The next particle is going to be moved to the right because the sine curve is positive height. And I'm going to move it really far to the right because of how high the sine curve is at that point. The next particle, likewise, will have to get pushed far to the right because the sine curve is really high and positive, up. The next particle will be pushed to the right because the sine curve is up, but it won't be pushed very far. This particle is not being moved at all because the sine curve has a height of 0. This particle is moved to the left a small amount. And let me move that up just a bit. The next particle here has been moved to the left a far amount. This particle has been moved to the left a far amount as well. This particle has been moved to the left because the sine curve is down below, but the sine curve isn't very tall, so it's been moved to the left just a small amount. This particle hasn't been moved at all because the sine curve has no height. This particle has been moved to the right, but a small amount because the sine curve isn't so high. And this last particle has been moved to the right a far amount. Now what I'm going to do is I'm going to take this particle and I'm going to move it the way my arrow tells me to. Okay? Then I'm going to take this particle and move it to the end of that arrow. And I'll continue in this fashion. This one moves over to here. And then this one doesn't move, there's no arrow. This one moves over to here. This particle moves over to here. This particle moves a large amount over. This one moves a small amount. This one doesn't move. This one moves a small amount. That one moves a large amount. I'm going to clean this picture up by removing the vertical lines and the arrows. Look at what we have. We have a compression right here. There's the center of a compression. We have a rarefaction right here. The particles are all expanded, centered around this point. And right here we also have a rarefaction. If I take away the sine curve, it's a little easier to see. So, what have we learned? We draw sine curves to represent longitudinal waves. Importantly, we've seen that the nodes shown on the sine curve, here's a node on the sine curve, here's a node on the sine curve, here's a node on the sine curve. Those nodes correspond to particles with zero longitudinal displacement. This particle I didn't move. This one I didn't move. And this one I didn't move left or right. Another way to say this bottom point is like this. Nodes on the sine curve correspond to nodes on the longitudinal wave. The final important thing we've learned, I'll put right up here. Nodes like here, here, and here, not only are they places where particles don't move, but those spots here, here, and here, those are where compressions and rarefactions are centered or where they occur. So if we clean this up just a little bit, here are the three main bullet points that we've just taken away, and these bullet points show us the link between transverse sine waves and longitudinal compression rarefaction waves. And now we can really appreciate that the sine curves we draw in, the transverse waves, actually represent longitudinal compressions and rarefactions. These represent sound waves.